they get into the press, unfortunately it's not always the breakthroughs you would like. So we're going to hear about the other kinds of breakthroughs, hoaxes, frauds and delusions, as well as real breakthroughs today tonight. Thanks, David.
Well, ladies and gentlemen, thanks for coming on this very cool night. I decided to give this lecture after my term as the President of the Australian Institute of Physics, because during that term, it was part of my job was to receive, sorry, that's probably too much. It was part of my job to receive correspondence from the public on their breakthroughs. They were having trouble getting into the standard physics journals, and they wanted me to help. And so over the Einstein International Year of Physics, I got to process a very large number of these discoveries, and I now have a very thick file. I'm thinking of organising a conference on some of these breakthroughs, but I'm afraid there's not quite enough physics in them to justify that. So my experiences, though, made me think, well, what is it that I could identify, or what are the general characteristics of physics that isn't a breakthrough? How do I know when physics is good and when physics is bad? And hence tonight's lecture. And many people have been down this path before me. So this is my plan for tonight. I want to start off by talking about historic breakthroughs that weren't. A very small list. And from those, I want to identify how to recognise pathological physics, that is to say, physics that isn't real. And I'll go on then to talk about some recent breakthroughs that weren't breakthroughs. And I want to wrap up then with what I call Jamieson's corollaries. These are the criteria by which you can assess whether physics is right or not. And of course, Asimov's axiom is worth mentioning at this point, together with Sagan's stipulation and the great Occam's razor. So when I started planning this lecture and came up with the title, some of my colleagues, including my head of the department, said, gosh, you really shouldn't be presenting dodgy stuff to the general public. You might confuse them. This is the school of physics. This is a bastion of truth and enlightenment. So in order to help you see when I'm presenting dodgy stuff to you, you ever see this symbol in the corner of the slide? Just don't take this stuff seriously, okay? It's all dodgy. But the upside is if you see the mortarboard in the corner of the slide, you can trust it. It's like dead when it's okay? Okay. All right. Now, in researching tonight's lecture, I found an enormous literature, and I just was getting overwhelmed with stuff that I could have selected to present to you tonight. And I had to draw the line somewhere, otherwise we would have been here till breakfast on Monday. So I decided I wouldn't present to you any stuff that was not even wrong. Now this expression, not even wrong, was applied by Wolfgang Pauli to a paper that he received to comment on in that, and he used this expression to say, well, there's nothing in this paper that can be of any value whatsoever. It's not even wrong. I can't even begin to critique the problems with it. In other words, the concept is not falsifiable. So if I say there's some Zeusian-style deity that controls our fates and everything is at the whim of that deity, then I can't do physics because there are no rules that I can uncover if the universe operates by whim. So this is one of the boundary conditions that tonight's lecture. I'm looking at stuff that is, say, plausible, but wrong. I'm not looking at stuff that's not well posed enough to not make specific predictions that we can test. So that's the boundary conditions. And of course, all the work, all the labours of the vast number of people who will appear here tonight are human. And humans are capable of enormous genius and the reverse. So on the one hand, we have truth and its partner, free and open inquiry. And on the other hand, we have fraud and delusion. And this always seems to be accompanied by secrecy and obscurity. But when you shine a bright light on it, you find out what's wrong with it. So these are the two great themes of my lecture here tonight. And sometimes I have to protect the identity of the people involved so as not to be liable to any slander legal cases. So when you see the black box, you know I'm protecting someone's identity. All right, so let me begin. Perpetual motion machines. These are historic breakthroughs that definitely weren't. And when I was a young lad, I had a book on science, and this proposal for a perpetual motion machine was in my book, some of my books that I had, and I was quite taken with this. This book was given to me for Christmas one year by my mother, who I'm pleased to say is in the audience tonight. And in this proposal for a perpetual motion machine that I thought looked quite plausible at the age of 7, you take a giant magnet, and here I've got a giant magnet in the theatre tonight, and you take a steel ball and you put it at the bottom of this ramp, and when you let the ball go, the magnet pulls the ball up, whereupon it falls through a hole at the top, rolls down, comes out the hole at the bottom, and repeats forever. So here is a magnetic perpetual motion machine. Now, I tried to build one of these for you here tonight, and I'd like to demonstrate it to you. First of all, let me put in a bit of physics. You notice the waterboard has just appeared there. If we now look at the forces that are acting on the ball at the bottom of the ramp, of course we have the downward pull of gravity. And if we're going to make a perpetual motion with this method, we have to balance the downward pull of gravity with the upward pull of the magnet. So let's resolve the gravitational force into a component pointing down the ramp and a component pointing at right angles to the surface of the ramp. And the only one we have to worry about is that blue vector that's pointing down the ramp. We have to balance that with the pull of the magnet to pull it back up the ramp. So in other words, we need this vector here. Blue laser pointer, guys. First one in Australia. Cost me a fortune to get it here tonight. It only arrived by Federal Express in the mail this morning. So here's the magnetic force on the ball bearing at the bottom. There's the equal and opposite force exerted by the magnet. And so if we adjust the pink vector here so it's equal and opposite to the blue vector here, we just might get this to work. Now before I energise the magnet, this is probably the strongest magnet in the building when connected to a giant power supply that's in the basement. So before I energise, I have to remove all the things that could be damaged. So I've got to take my phone out of my pockets, my wallet, my keys here in case they get dragged out of my pocket by the magnetic force. I have to take my watch off. I'm sorry about this. And also I have to, it's hard to get out, I have to take out my pacemaker. Alright, so now I'm ready to go and get ready for action here. And I should say, if any of you gentlemen have pacemakers in the front row there, there's a possibility that I'll go into save mode when I energise this magnet. Alright, yes, please come in, folks. I should mention, for those of you who are sitting or standing, we're piping the lecture into the Hercus Theatre, which is right next door. You can get to it by going through the door up there if you want to sit. And it's only a few metres away, and if we open the doors, you can still see me through the doors. Okay, so we'll now energise the magnet and see if we can get our perpetual motion machine working. Now, I forgot to ask Nick, how do I turn this? Oh, yes, here we go. All right, so I'm going to turn this to maximum, because there's no sense in mucking around here. And I'll now put the ball on the ramp. Unfortunately, oh! Okay, so... Okay, I just want to run that again for you. That was a little too quick. It was pulled out of my hands. So this is about a 2-student magnet. I'll just de-energise the magnet for a second. Oh, there you go. Alright, I'll re-energise it. Okay, but you can see the problem. As the ball is pulled by the magnetic force, it's far too strong to let it fall back down through the hole at the top and return to the bottom hole and repeat the cycle. So this proposed perpetual motion machine, which I've always wanted to build from a very early age, I had my opportunity here tonight, doesn't work because the magnetic field, of course, increases as you get closer to the pole. And so this little pink vector soon becomes this massive pink vector, 25 times bigger once you get closer to the magnet. And as you've seen, even someone as strong as I has trouble pulling the ball bearing off the magnet with this amount of current flowing through it. So I'll just turn that off again so that the pacemakers in the front row can return to normal feedback operation. Okay. So this perpetual motion machine cannot work. That's a pity. However, there's another topic which I've been very interested in since a very early age, and that's space travel. And the web is very rich on proposals for reactionless space drives. This is now some examples of delusions. Now, what is a reactionless space drive and why is it problematic? Well, let's quickly just review Newton's laws of motion. The one I want to concentrate on here is the third law. For every action, there is an equal and opposite reaction. So in other words, if I propel myself across the lecture theatre, my feet are pushing on the surface of the planet, and as I go forwards, the planet goes backwards. However, the mass of the planet is enormously greater than my mass, so the amount of distance the Earth goes back is tiny and unmeasurable compared to the amount of distance I go forward. Nevertheless, this is a real effect. And every type of motion involves action and reaction, except reactionless space drives. Now, this is an early version of me testing Newton's third law during a break at school with a couple of cohorts. You'll notice it's not me about to push the button here to send the rocket into orbit. I'm standing behind one of those trees because every now and then that happens. And I can assure you Newton's third law does apply, except there's no net motion in this case, but the force vectors are uniformly distributed in all directions at once, and you can see some fragments flying out here. However, this shows the principle by which reaction in rockets works. You start with a rocket that's full of fuel, and you throw the fuel away as quickly as possible, and so the fuel goes backwards, the rocket goes forward, conservation of momentum. And the difficulty with rockets using reaction like this to propel themselves, if you want to get into orbit, you need to travel at a speed of 11 kilometres per second, otherwise you fall back to the surface of the planet. And the best chemical rocket fuels can only be thrown away, that is the exhaust, can only be thrown away at a rate of 3 kilometres per second, a speed of 3 kilometres a second. So when you do the maths and derive the rocket equation, you find that if you're going to go into orbit with a single rocket, single stage rocket that throws its fuel away to make the rocket go up, you have to throw away 98% of the mass of the rocket in order to get the remaining 2% into orbit. And this is a daunting ratio, and this cannot be achieved with conventional fuels for a single stage rocket, and hence the idea of 3 or even more stages where you actually throw away most of the rocket as well as all the fuel. Now, wouldn't it be great if we had a reactionless drive so we didn't have to throw anything away? I can't tell you who this gentleman's name, but he invented a thing called a Dean drive. Anyway, he has a very nice website which I've studied very carefully, but I just don't understand how his Dean drive works. However, after intensive research, I think I figured it out. And his mechanism for a reactionless drive was boosted by the editor of astounding analog science fact and fiction magazine, who promoted this very heavily. And here's an artist's impression of a submarine, which would be a very good spaceship, propelled to Mars with a Dean drive inside there somewhere. So I was very puzzled as to how this would work, and I was very taken with this science fiction story by James Blish when I was a young lad and had more time for reading these sorts of things. James Blish had conceived of the spin-dizzy space drive, in which you harness the angular momentum of the atoms in your spaceship, and with this reactionless drive and that enormous amount of angular momentum inside an average lump of matter, you could lift entire cities into orbit. And I don't know how this works. However, after intensive study of Norman Beak web page, I've come up with a reactionless space drive, which I'd like to demonstrate to you for the first time here tonight. Unfortunately, I can't show you what's in here because if you wanted to inspect the Dean drive, you had to pay an inspection fee of several $100s. And so I think, given the financial situation of the school, we'll use the same rules here. But I can assure you it does work. I've studied the situation very carefully, and watch this. Here we go. I'm going to turn on my reactionless drive. First of all, I'll emphasise there are no wheels sticking out the bottom, which would propel it across the floor, and there are no rocket motors sticking out the back. Okay, so it's entirely self-contained. So let me just turn it on. I'm not sure which direction it's going to go. Okay, there it goes. It's moving towards me. It's going to take a long time to get to Mars using this technique. And I can emphasise that once you get to Mars, you'll be able to come home again because it works just as well in the opposite direction. Which is to say, not very well either. And it does seem to move in circles simply because the plastic box I mounted it in is not perfectly square. Now, this is breaking the laws of physics. This is breaking Newton's third law, because here we're getting a net action without a reaction. So this looks like a reactionless space drive. The speed is perhaps within reach. However, the same book that I got the designs for my model rockets from was written by a physicist, and he said if you're ever approached by someone with a reactionless space drive like this, here's a simple test to see if it is really a reactionless space drive. Hang it up on a piece of string. I happen to have a bent paper clip and a bit of string to hang my space drive on, and turn it on and see if it goes anywhere. Because, of course, it was moving along there. Did anyone see all this? No, thank you. So let me just hang it on the string, and if it really is a reactionless space drive, it should whiz round and around violently at high speed in a big circle as it propels itself through space. So here we go. Okay, it didn't work. In fact, what I've got in there is simply a mass, an eccentric mass going around in circles, being very violent. And what we're seeing here is, you can have a look inside for free later on if you want, and we're seeing the difference in the coefficient of static friction versus the coefficient of kinetic friction, and there's the reaction is on the axle of the motor in there as the eccentric weight goes around. So unfortunately, my sensitive test of the reactionless space drive revealed that Newton's third law is still true, and I don't know whether Norman Beak ever did that on his machine. I suspect not. Now I want to turn from Newton's laws to the laws of thermodynamics. And quite often, dodgy physics breaks, usually not the first law, because everybody knows that energy is conserved and cannot be created or destroyed. But the second law goes hand in hand with the first law, and I find that in our society, the second law is not widely understood. The second law basically says it's impossible to convert heat completely into work. And as you know, when things get colder, they contain less heat energy. So couldn't I make a refrigerator by using the heat energy in a lump of warm food to power the motor that cools it down to low temperatures? Why hasn't anyone invented such a fridge that uses its own internal heat? Its conservation of energy would allow that, but it breaks the second law. So what's the second law? Well, the second law basically says, in simpler terms, that not all energy is useful. And here's a practical example of that. Here's a mobile phone. My phone, the battery died just before the lecture, so I don't have to remind myself to turn off my mobile phone, but perhaps it'd be a good time to turn off yours, by the way. And this battery needs 10,000 joules of energy to be fully charged. Now over here I've got a bathtub full of hot water, and that bathtub is at a temperature of 60 degrees Celsius, it's quite a warm bath, and if it cools to the ambient, sorry I made this in the summer, that should be 5 degrees, so we might get a little bit more energy, but when it cools to ambient temperature, say 20 degrees, this bathtub with half a cubic metre of hot water in it will release 80 million joules into the environment. So all I need is 10,000 in order to charge my phone. What is the problem? I could charge every phone in Melbourne with my bathtub full of hot water, but no, I cannot, because the second law says that I cannot tap all of that energy to do useful work. It's too disorganised. And in fact, if you do the maths, you find that you can tap less than 8% of that energy into useful work because it's so disorganised, and you need your energy to be organised for the phone. Now, Hollywood is great at breaking the second law. I used this slide in my first year advanced mechanics lecture, and I'm afraid my students, I tested them with the little story I'm going to tell in just a moment, and they didn't identify the most serious error in the little story I told them based on this picture. So let me tell you the story. There's a Hollywood movie which is called The Incredible Bulk. And the superhero Bulk is played by an Australian actor called Eric Banana. Now, the Bulk encounters a supervillain called the Green Hornet. And as the Green Hornet is about to attack the Bulk, the Green Hornet runs out of energy and he becomes a pale shadow of his former self. However, he spots down below a lake of water. He dives into the lake and extracts the heat energy from the lake, thereby freezing it, and returns to continue fighting the Bulk. Now, what is wrong with that story? Yes, I know it's not Eric Banana. Yes, I know it's not the Bulk, but I also know that this breaks the second law. So that isn't going to work. Now, the penguins don't like it either. Yeah, another example of the second law is in this jar. I prepared this very carefully while I was having my dinner this evening. In this jar, I have got a layer of Maltesers, which are the brown spheres here, and a layer of M&Ms. And these are very highly organised. I've got the M&Ms well separated from the Maltesers. So this is equivalent to the concentrated energy in my mobile phone. Now I'm going to randomise it by doing all sorts of erratic things. And I put too many in. I'll just take a few out so I'm not shaking it here all night. I've got something I can tip these into. I'll keep shaking while this... So, okay, we're getting pretty random here. Oh, good on you, mate. Put that down on the school physics box. Okay, thanks. So, anyway, after quite a bit of random thermal agitation, I now find instead of having a beautifully separated, organised configuration of Maltesers and M&Ms, I've now randomised them. Now, if you saw how that was at the beginning and saw how it is now, it's the same amount of energy in both configurations. But this is not a special configuration, this is a random configuration, whereas the one I started with was random. Now, if you try and break the second law, it's equivalent to somehow being able to pick out the myriad different configurations of the M&Ms and the Maltesers in this jar and just pick out the one you want. It might be because you want to eat all the M&Ms first before you eat the Maltesers. So. But that will break the second law, and you have to put in energy in order to do that. But I've discovered a special way of shaping this, which breaks the second law. Let me demonstrate to you. Oh, sorry. You've got to get the wrist action exactly right here. Not quite, hang on. It's just not working. Okay. You'll have to see me later. Okay. Now, conservation laws are not just arbitrary laws that physicists have invented in their spare time. All conservation laws arise from fundamental underlying symmetries. And so the conservation law is just a consequence of a fundamental symmetry of space and time. So, for example, the conservation of energy arises from the fact that the laws of physics do not change with time. So if you say you've discovered a way to break conservation of energy and suck energy for free out of the ether, then you're really saying, I found that the laws of physics are not symmetrical with time. And if you say I've got a reactionless space drive, then you're saying not just that you've broken the conservation of momentum, but you've found that the laws of physics don't depend on position. They're different here to what they are over there. And likewise, the conservation of angular momentum and even the conservation of electric charge and other conservation laws depend on fundamental symmetries. And that's why they're very hard to break, because these symmetries are very fundamental to the way our universe works. Now let me turn to Irving Langmuir, who was the inspiration really for this lecture, because Irving Langmuir, who was a Nobel laureate, published criteria for assessing pathological physics, which I just want to mention now. Nobel laureate in 1932 for surface chemistry. He invented with his collaborator, who I think she did most of the work, the Langmuir-Blodgett film, which is a way of putting down monolayers of molecules on surfaces. He coined the term in 1953 pathological science, which is research conducted with accordance to the scientific method but tainted by unconscious bias or subjective effects. And he was often called upon to investigate paranormal or flying saucers, which were big during the Cold War era of the 50s, but seem to have faded out a bit today, notwithstanding the celebrations at Roswell a couple of months ago where 30,000 people converged to continue to investigate the flying saucer crash. He, in this very influential lecture, he presented a few case studies for what he considered was pathological physics. The first one he presented was historical from 1903, the discovery of N rays. Now at this time, physics was in an enormous expansionary phase. Radioactivity had just been discovered, X-rays had just been discovered, alpha rays had been discovered, beta rays had been discovered, gamma rays had been discovered, even delta rays had been discovered in solid-state physics, so why not N rays? This is what Professor Blondlot claimed to have discovered. He found that if you took a hot filament and covered it with a sheet of quite thick aluminium, you could detect rays that emerged from the hot filament that then fell upon an electric spark or a thin piece of cardboard, and it caused the brightness of the spark or the illumination of the cardboard to change a little bit. And you needed an aluminium prism to refract the rays in order to do this experiment, because it only worked at a particular angle. And this was extraordinary. It was a bit of a worry that you could only see these effects if you turned the lights in the room right down. And it was only just barely visible. And an American investigator in 1904 came across to learn more about N rays, because there was a pile of papers in the scientific literature, including the journal Nature, which is every physicist's ideal to get their work written up in Nature, on the characteristics of N rays, quite a serious literature. And Professor Blondlot claimed that you could not only see them from a hot filament, if you left an ordinary lump of metal like a file out in the sun, it would absorb N rays from the sun and emit them, or indeed living things seem to also emit N rays. N rays were then hailed as the triumph of French science. The American, however, Robert Wood, came across and he was most intrigued. And while in the darkened room, Professor Blondlot was reading out the angles where the N rays were being refracted through the aluminium prism from this file which had been prepared by lying in the sun, Professor Wood removed the prism and put it in his pocket. It made no difference to the position of the refracted beam of N rays. And then while Professor Blondlot was continuing to read out the intensity of the N rays, Professor Wood also removed the file. It made no difference. There were therefore no N rays and no more Professor Blondlot. So Irving Langmuir said, well, we saw that the problem with N-rays was that the maximum effect, that is the very slight brightening of the spark or the slight illumination on the card, was barely observable. You needed to have expert vision in a darkened room in order to see it. And if you doubled the size of the file, or you put 10 files or a house brick or 16 cucumbers, it didn't make anything brighter. So the effect did not scale with the intensity of the cause, and that was a danger sign. It was also very hard to see. Only Professor Blondlot seemed to be able to see it, yet he seemed to be able to measure the angle of refraction with great accuracy. Then there was the rise of polywater. Now this was discovered sometime before 1966 in Russia. The workers found that if you put water into a small tube, it seemed to boil at 150 degrees, freeze at 40 degrees below, and be about 10 or 20% denser than ordinary water. And hundreds of papers on this phenomenon appeared in the 1970s. And in fact, Kurt Vonnegut used it as the inspiration between Ice 9, this chilling story, Cat's Cradle, which is a science fiction novel, but nevertheless got him a master's degree in anthropology at the University of Chicago in 1961. And I should mention that Vonnegut died, I think, last year. Now, here's the inspiration of the physics community for explaining polywater, and Vonnegut's inspiration for Cat's Cradle was to say, well, maybe water molecules can pack together in different ways, and the way they're packed together, perhaps in ordinary water, there's a glass over there, which I'll get to in a minute, can be rearranged to find a more efficient packing arrangement. Now, here I've got a pile of tennis balls, and these are packed together in a particular way, but by making a subtle rearrangement, simply by moving things around a little bit, I can change, I won't do it, I can change the arrangements a little bit. I can't do it with this particular arrangement, I need to take a couple out, but nevertheless you can imagine trying to pack these into space a different way. And so this was the story of polywater. Now, ordinary water exists as a solid, a liquid, or a gas. And this, by the way, is where Mars, Earth, and Venus sits on this diagram of temperature versus pressure. And Vonnegut's Ice 9, the topic of his Cat's Cradle book, was proposed to be a new phase of water that fitted in here that froze at 45 degrees Celsius, 45 degrees above zero. So if you dropped a crystal of Ice 9 into the oceans of the Earth, the arrangement of the water molecules in Ice 9 would show the oceans of the Earth how to rearrange themselves to make this solid, and the whole planet would freeze solid in an instant, which is what, I won't tell you what happens in the book actually. There is a real Ice 9, by the way, which is a phase of ice that's formed at very high pressure. However, Ice 9 unfortunately does not exist, and let's get back to polywater. Some serious journals published some worrying articles, polywater or anomalous water, or was it really impurities? And this guy, I don't know who this is, but he was speculating that maybe Venus was a polywater planet. However, the number of papers rose to a maximum in the early 70s and then suddenly died away. And the reason why they died away is because careful chemical analysis revealed the water in the capillaries that the Russians had been studying was contaminated. It was not pure water. In fact, it was more like sweat. So that when you did the experiments with ultra-clean glassware, no anomalies were observed, and eventually the claim for polywater was withdrawn, and it disappeared in the mid-70s. So Irving Langmuir added a few more symptoms. You needed a fantastic theory from some hitherto undiscovered packing arrangement for water, and the people working on it were sincerely motivated, but they had to keep changing their story every time someone did an experiment that showed it didn't exist, until eventually the whole concept of polywater vanished. Well, so much for delusions. Now let me turn to fraud, the story of super heavy elements. Now, if you look inside the nucleus of an atom, you find neutrons and protons. And not all arrangements of neutrons and protons are equally stable. In fact, nature doesn't like odd numbers. And so, for example, if in this snapshot of a sort of expanded version of the periodic table, where I've got the number of neutrons in the nucleus are on the horizontal here and the number of protons in the nucleus along the vertical here, we can see that the number 20 is a particularly convenient arrangement, a particularly favourable arrangement of protons and neutrons, because the element calcium, which has got 20 protons in the nucleus, can exist with all these different forms that have different numbers of neutrons. Here we've got 22, 23, 24, and 25. And this number of neutrons can exist in chlorine, argon, potassium, or the calcium I've already mentioned. But up here, poor old scandium, with 21 protons in the nucleus, only has one isotope, as these are called, and there are no other stable configurations. And down here, potassium's a bit dodgy because it's got 19 protons, and one of them is unstable. And all the white ones are not found in nature. And as a young aspiring physicist, I was quite impressed with this, because if you turn now to the case of aluminium and copper, here's a rod of aluminium, and that came up very nicely with the grass, so thank you. And in this rod of aluminium, every single aluminium atom is identical, with 27 nucleons, that's to say protons and neutrons in the nucleus, because that is an odd Z nucleus. However, this rod of copper contains a mixture of atoms. They're not all identical, a mixture of isotopes. 69% of copper 63 and 31% of copper 65 with 2 extra neutrons in the nucleus. So they're not all identical because of this odd and even issue. And if you go right up the periodic table to the top end, we look around Z equals 92, there are no stable configurations of protons and neutrons, and so the uranium isotopes, the thorium isotopes, and the artificial plutonium, and indeed the americium that we all have in our homes, in our smoke detectors, are all unstable. However, it's known that 20 isn't the only magic number. The numbers 114, 120, 126, and 184 are also magic. And by magic, I really mean that quantum mechanics says that when you pack quantum mechanical particles in together in these numbers, you form particularly tightly bound and particularly stable configurations. And so this led to the prediction that way beyond the island of thorium, uranium, and its isotopes on this diagram, which is here in the sea of instability, there may be an island of super heavy elements with these magic numbers of protons and neutrons, which didn't exist in nature, but was nevertheless particularly stable and favourable. And so people have been trying to make them. The typical idea is to accelerate up a xenon atom to enormous speeds, smash it into a mercury atom, whereupon a violent nuclear reaction takes place, and a calcium atom is spat out, and a couple of neutrons, and you're left with this super heavy. This is the basic idea. Most of the time, this shatters into a million pieces. However, sensational reports of the discovery of super heavy elements with this method appeared in the literature back in the 1999, in the early 2000s. First of all, Darmstadtium, Roentgenium, and Ununium were discovered in Germany. And then the same method, after the Americans recruited the guy who was responsible for designing the experiments to California, to the Lawrence Berkeley lab, and put him to work, he suddenly discovered Ununoctium and Ununhexium. And this was sensational, major press release, Americans discovered new elements. However, in 2001, no other laboratory was able to reproduce the results using the same method. And this triggered an inquiry in 2002, and eventually the Lawrence Berkeley lab was forced to retract the discovery of element 118 and 116, and the individual who made the discoveries, who turned out to be the only guy who knew how to interpret the very delicate data, very low signal-to-noise ratio, very rare to produce a super heavy with this very violent process, had fabricated the data. I should mention the Russians heroically kept going, and in 2006 really did discover a number of element 116 and 118, and hence they can give them proper names instead of these temporary ones. And the Germans reinterpreted the data for the discovery of these, and they found that although some of the data had been altered, it didn't affect the conclusions. So unfortunately, these super heavies in 1999 was an example of fraud. Now let me turn to an example of delusion in the field of nuclear physics. I want to talk about the strange case of nuclear isomers. Now, what is a nuclear isomer? Well, some atoms, some nuclei, have a very strange attribute. In the ground state, when the nucleus is just lying around in its lowest energy configuration of packing protons and neutrons, it's more or less at rest. It could be spinning very quietly and gently and not too noisily. But you can spin the nucleus up by hitting it with radiation, and you can spin it up actually so that it spins with enormous violence because it's held together with enormously strong nuclear forces. And this can create an excited state. And this excited state of the fast spinning nucleus can decay back to the ground state by emitting a gamma ray. So this is an energy level diagram. Here's the spinning nucleus, here's the resting nucleus, and the difference is radiated away as a gamma ray. And by analogy, I can introduce this balloon here. And you can consider this to be the nucleus in a relaxed state. Okay, not a lot of energy here, just very, very limp. But I can pump it up. And now it's got quite a bit of energy. And I can easily release that energy by letting it go. Oh, I'm terribly sorry. Free admission at all future July. However, there are some nuclei that have a very strange, oh, there's the gamma ray heading off. There are some nuclei that have a very strange property that they get knotted. And when they get knotted, the energy cannot escape. And so they can sit for quite a long time in this unnatural, highly spinning state. And one such nucleus is hafnium-178, referring to the number of protons and neutrons in the nucleus. And it actually has two possible knotted configurations. And this is a very complicated energy level diagram. And these numbers refer to how fast it's spinning. There's one up here, which is so knotted that it can only very gradually get unknotted by radiating a particularly knotty type of gamma ray. I'm pushing the analogy a little hard here, but you get the idea. So that it takes, in a sample of 100 hafnium isomers, as this state is called, it takes 31 years for half of them to get unknotted and decay back to the ground state. And it does so by passing through this intermediate state, which is also a little bit knotty, but that decays with a half-life of only 4 seconds. So I've got here a basket full of hafnium isomers, not to scale, but you get the idea. And if I stood here for 31 years, half of them would have spontaneously decayed down to the unknotted state. Now, there were sensational reports in literature that it was possible to irradiate the hafnium isomer in its knotted state with a very feeble bit of radiation called an X-ray. So an X-ray is like a gamma ray, but very feeble on the nucleus sample. And these X-rays were thought to lift the isomeric state, lift the isomeric state up a little bit to a different configuration of spin. And this would then allow the long-lived isomer to decay to the short-lived one, and then 4 seconds later down to the ground state. This was an incredible claim because it's very unusual for very weak radiation to unlock the enormous energies inside the nucleus. But I can do it for you here tonight. Here I've got my X-ray. There I've got my basket full of hafnium isomers. And if I throw the X-ray into the hafnium, gentlemen, if you do have pacemakers, set them to turbo mode now. An enormous amount of energy is released, triggered by the impact of my very feeble X-ray. And that was so nice, it's worth firing another X-ray in just to make sure that it's reproducible. Oh yes, very reproducible. So the guys who discovered this said, look, we've got a way of using an X-ray which has an energy of only thousands of electron volts to trigger the release of gamma rays which have energies of millions of electron volts. And there they go. Here's the data. Now I find this a little bit unconvincing. Across the horizontal axis here is the energy of the X-ray going in. And across the top here is the difference between the gamma ray spectrum with the X-rays off and the gamma rays with the X-rays on. And you've got to remember that these things are decaying away by themselves with a half-life of 30 years. So there's fierce gamma rays coming out of here all the time anyway. They're spontaneously popping at a leisurely rate. And this was supposed to be the peak due to the enhancement caused by the X-rays. This led to this idea, that you could take a golf ball-sized lump of the hafnium isomer, pumped up to its excited state, fit a tiny little X-ray trigger into it, and this would release uncountable amounts of energy, quite well uncountable actually, 1.3 billion joules of energy per gram of hafnium isomer, the golf ball nuclear weapon. 10 tonnes worth of TNT in every golf ball. So needless to say, the military were very interested. The physicists were not. Because this experiment was repeated in another laboratory, this time pumping in X-rays not from a dental X-ray machine which the lone researcher had used to make the discovery, but from the incredibly intense X-ray beam from a synchrotron. And by blasting the hafnium isomers with the synchrotron X-rays, you would expect to see peaks corresponding to all the gamma rays that come out when the hafnium isomer decays. And here's the data, the difference between the X-rays off and the X-rays on, and no such signals were observed. The effect could not be reproduced even though the X-ray intensity had been enormously increased, the equivalent of all of you having your own X-ray and chucking it down into the basket. So this has now been discredited. The military is still putting money into it. Hydrogen cars. A few years ago, up in Queensland, Joe Peterson announced a triumph of Queensland physics, the world's first hydrogen-powered car that was going to solve all our transport problems. And he was going to spend an enormous amount of money commercialising this Queensland discovery. There's a slight sound of N-rays here. The car, I've researched this carefully to see if I can understand how this car works. And I've downloaded the patent from Stephen Beach. And this patent is chock full of very helpful diagrams. And as far as I can understand, this is the essence of the idea. So you didn't need all those helpful diagrams. This is the idea. You take a small battery. You connect it up to 2 platinum foils in a bucket of ordinary water, and you get electrolysis. And you take the hydrogen off the cathode and you put it into the fuel intake of your car. And, oh, sorry. And voila, off you go. Now, I'm really puzzled by this, because energy conservation says that why do the electrolysis in the first place? Why not just connect the battery straight to the wheels of the car? And that's not the only trouble with this idea. It can't work. Conservation of energy says it can't work, and unfortunately I don't have my hydrogen electrolysis powered car here for you tonight. We did buy one, but it died just before we set it up. But I found that the conversion efficiency from the electric current into the electrolysis into the hydrogen out that powered the car had an efficiency of about 2 or 3%. So this cannot work. Nevertheless, while I was preparing this lecture, I saw this quote in The Age on July 11 from someone from the CSIRO. You can expect in a few years' time lots of houses will have solar generation from panels on the roof and a little wind turbine on the roof maybe, and that opens the door to charging the vehicle for free and absolutely emissions free. Fantastic. So I thought I'd do a few calculations of my own. The energy content of one tank of petrol petrol has about 34.2 megajoules per litre, is in a 70-litre tank in my Porsche Cayenne, in my dreams, is about 2.4 billion joules, 2,400 megajoules. That's an enormous amount of energy. Now, the sunlight on the roof for about a day, keep it in mind on a Porsche Cayenne, I have a very large roof. Solar input here in Melbourne occasionally reaches 1,400 watts per square metre at 12 noon on the longest day. The rest of the year it's much less. And let's assume you've got 50 square metres of solar panels and they have an efficiency of 10%, which is pretty good, better than a Dick Smith solar panel, I have to say. And that they work for 4 hours a day. Keep it in mind the sun rises and sets each day. And in the early morning and in the late afternoon, the angle of the sunlight is very low and not very helpful. This turns out to be 100 megajoules per day. So to get your 2,400 megajoules for one tank of petrol, ignoring the conversion efficiency of the electricity into kinetic energy, you need 24 days to get one tank. In practice, you'll probably need more like 50. So that is a fairly relaxed sort of but not impossible if you're prepared to wait. Now, I'd like, in my second last example, to turn to the internet. Now, the internet is a marvellous source of hoaxes, frauds and delusions. It's just unbelievable, the rich source of this material, and unfortunately I had to reject hundreds or even thousands of things I found on the internet and just focus on one. Now, I have a large number of friends who are worried about getting cancer from their mobile phones. And it doesn't seem to matter how much I explain to them the difference between ionising and non-ionising radiation. They're always sending me things like this. I found this on the internet, it must be true, so there. This arrived just 2 weeks ago. Cooking eggs and mobile phones you need, and it was a very nice Word document, beautifully illustrated with nice fonts. Very persuasive. You need an egg and 2 mobiles. You use the mobile on the left to call the mobile on the right, with the egg in between. Then the radiation clearly goes backwards and forwards between the 2 modes, passing through the delicate proteins in the egg. And after, okay, fair enough, nothing will happen in the first 15 minutes. This is to dissuade people from trying this at home because they might be impatient and not be prepared to run up a large bill. But after 20 minutes, apparently the egg warms up, and after 45 minutes, the egg is already hot, and after 65 minutes, the egg is cooked, and so is your bank balance from your mobile phone bill. And so the conclusion of this experiment, in inverted commas, is that microwave radiation emitted by the mobiles modifies proteins in the egg. Imagine what it can do to our brains. Well, let's analyse this using the laws of physics. No, that's not the outcome I was expecting. Mobile phones put out about 250 milliwatts at a frequency of 900 megahertz in general. Some are different frequencies. And actually the resonance energy from most efficient absorption of microwave radiation in water is 2.45 gigahertz. And a microwave oven pumps out about 1,000 watts at this exact frequency, and that's the equivalent to 4,000 mobile phones. So you might succeed in cooking your egg with this method, but you'll be waiting for a long time. Or just increase the number of mobile phones to 4,000 and leave them for longer. All right, now for the big one to more or less wrap up here. Fusion. Fusion hot, fusion cool, and fusion cold. And this is under the topic of delusion, frauds, and hoaxes. First of all, a bit of physics. The strong nuclear force holds the nucleus together. So if I have a proton and I have a neutron, and I put them together, they'll stick together by these strong nuclear hooks that stick out of each one and link them tightly together. However, these hooks, as you see in my diagram, are very short, so they've actually got to get very close before the hooks can engage and stick together. This is not a force that extends for very far in space. That's fine for a neutron and a proton, or two neutrons to stick together, but it's a bit problematic if you've got two protons, because two protons both have the same charge. They're both positively charged and they repel each other. You've got to really push them against the Coulomb and push them to Coulomb. There you go. And now they're put together with a strong nuclear force. And in fact, it's still a bit dodgy. You're really better off having a neutron in there as well, just to provide a bit of extra strong nuclear glue to make that stable. So it's a big problem if you want to fuse light elements together, like what happens in the sun, to make heavy elements. And they're the force diagrams to function of distance. Here we see between two protons, you get the repulsive force until you overwhelm it, and then they stick together. Fusion invariably involves isotopes of hydrogen. So let me just explain that for a moment. We have the most common form of hydrogen is just a single proton with a single electron in orbit. This diagram, of course, is not to scale. The proton to the electron orbit is the same scale as a dust mote floating inside a cathedral. Very small nucleus, very large electron cloud. But hydrogen also exists in the oceans of the Earth and everywhere else in an alternative configuration where a neutron has got stuck onto the proton, and this is called deuterium or heavy hydrogen, and about 0.015% of all the water around the place is this isotope of hydrogen, including the water in this glass. It's slightly enriched around the Japanese nuclear power station. But only slight, and I doubt if you'd be able to detect it. Tritium is another form of hydrogen, in which case there are two neutrons in the nucleus, but this is unstable. There are too many neutrons, it decays with a half-life of 12 years. Now, by joining hydrogens together, you can release energy. And in the sun, we have the first type of fusion I want to talk about, hot thermonuclear fusion. Now, you might expect hydrogen, the most abundant element in the nucleus, will just join them together and make something else and release energy. But unfortunately, all the likely joining togethers do not release energy. You've got to force the hydrogen together to make this isotope of helium, and you don't get any energy back in return for the amount of work you had to do to create it, nor these other possible nuclear reactions. So none of these reactions occur in the sun spontaneously or anywhere else. In the sun, the sun uses something more exotic. It bangs the two protons together by virtue of the heat, and then something strange happens. One of the protons decays into a neutron and spits out a positron, an anti-electron, and a neutrino, and releases energy. So this process requires not only the strong nuclear force, but the weak nuclear force in order to convert the proton into a neutron. And of course, the weak nuclear force has the most salient characteristic that it is weak. And so this is very improbable. And in fact, for those of you who have got a classical education, if I took an ampere of beam current, an ampere of protons, not electrons, but protons, and fired them into a slab of solid hydrogen for 10 years, in that entire period of time, two protons would stick together, the neutron would appear, and I would have made deuterium. So one reaction for 10 years, a very improbable reaction. And so the sun is actually a very feeble nuclear fusion reactor because of this process. It's about 300 watts per cubic metre. Very feeble and not suitable for human power. You have to have a reactor, well, as big as the sun to get energy out of that. So what humans use is not that sort of hot fusion, but well, we're trying to do it, of course, with the new reactor taking place in France now. But it's much easier not to use the weak interaction, but to just use the strong interaction. And this gets us to cool fusion. Now, cool fusion is a term that applies to a different type of hydrogen. This one has a proton and an electron, but as Jeff Taylor explained 2 weeks ago, there's a different type of electron in nature called a muon, that is several hundred times heavier. And so you can make muonic hydrogen, which has the muon in orbit around the proton. And because the muon is so heavy, if you put it in orbit around a special type of hydrogen gas, which is made of deuterium and tritium instead of conventional proton and proton with an electron, here we've got tritium and deuterium with a muon, these two are pulled so close together that the strong force can come into play and they will fuse. So here's the process. Deuterium, heavy hydrogen, tritium, even heavier hydrogen. A muon goes into orbit. This is somewhat schematic. And a fusion reaction occurs. You get a helium nucleus spat out, a neutron spat out, a lot of energy, and the muon's available to try it again. So this is muon-catalyzed fusion, cold fusion. Unfortunately, this reaction proceeds at a snail's pace, and it's very hard to make muons, and so this is not useful for an electric power generator. But now we come to cold fusion. Oh, sorry. In cold fusion, we don't have any of those processes, the one in the sun involving weak interaction, the one with muons involving strong interaction. We have here something new, perhaps. In 1989, two chemists, not physicists, chemists, claimed to have discovered a new type of fusion. By coincidence and importantly, there was a rival group. They were at the University of Utah. The rival group was nearby at the Brigham Young University, who had the ideas at the same time, and they were sort of in competition or collaboration. And then due to a mix-up, where they were going to simultaneously publish their results, the guy at Brigham Young heard that these two guys at the University of Utah had made a press release on their discovery, and so he went public as well, and this triggered a great race. So on the 23rd of March, these two guys from the University of Utah in 1989 announced they had created fusion in a test tube. And this triggered 500 days of intensive global effort, including experiments done here by someone who will remain anonymous. Patents, lawyers were involved. This could solve the world's energy problems. Television interviews, $5 million of funding were immediately stumped up from the state of Utah to commercialise this famous Utah discovery, the whiff of N-rays in the air. And it was hailed as the greatest discovery since fire, and here are the test tubes in which the fusion is taking place. Oops, sorry, I should. Okay, so here, why did this happen? Well, this was all completely plausible at some level. Cold fusion has a long prehistory. In 1905, Einstein put forward E equals mc squared, and then in 1926, Zeppelins had to use hydrogen because of a shortage of helium, and hydrogen is much more dangerous. But with E equals mc squared, these German scientists figured that if we put hydrogen into palladium, and the reason for that I'll explain in a moment, we might be able to produce helium using E equals mc squared. And it seemed to work. And the Electrolux company in Sweden got involved, and they said, well, let's use electrolysis to enhance the process, and we'll have an inexhaustible supply of helium with this method. And they tried to patent it, but it was rejected because the patent office couldn't understand it. Then people discovered helium coming from hot springs. Chadwick discovered the neutron, and when deuterium was discovered, Electrolux company tried again with deuterium, but didn't succeed in producing helium in this method. Then a mad scientist in Argentina convinced the Heron to stump up millions of dollars to build a fusion start machine, which was one of the greatest scientific fiascos in Argentina history. And then in 1978, hot springs were discovered producing helium-3. And so here's the basic idea that stimulated cold fusion. Down inside the Earth, there's this naturally occurring deuterium in water. The Earth is hot, but not hot enough for thermonuclear fusion like in the sun, but maybe there's some kind of exotic chemistry which was forcing them together, and the helium-3 decay products were going out the volcanoes or up the hot springs. So here are all the different ways deuterium can be used. You can get helium-3 plus hydrogen. You can get, tritium plus hydrogen, which would then decay and emit a positron, which would be detected. Or you could get helium-3 and a neutron, and the neutron would be absorbed by water, and it would have 2.5 MeV of kinetic energy, some of which would be dissipated by causing the water to recoil when it was absorbed. Or you could have helium, ordinary helium plus a gamma ray, a very rare event. But all these things could be detected. So the idea in Utah was to take palladium metal, a precious metal, which has got the unusual chemical property that it loves hydrogen, and it can absorb 900 times its own volume of hydrogen if helped along by electrolysis. And the idea was that this very densely packed palladium lattice would absorb the deuterium, and in some places maybe the deuterium would get close enough to fuse together, and the decay products would then emerge from the test tube. The energy would appear as heat, and the helium-3 and the neutron would appear as evidence that there was a nuclear reaction occurring inside the palladium. And when challenged to do this, to do a control experiment with water, ordinary water, light water, it was found that it still worked. And so the explanation, an ad hoc explanation, was that, well, there's deuterium in ordinary water, and maybe occasionally two deuteriums will find each other, even though it's only 0.015% and fused. So that seemed plausible to me. So here's some data. Here's a test tube top view. There's it bubbling away, and these are hot spots claimed to be where fusion is occurring. I think they look like bubbles to me from the electrolysis. And here's the spectrum of gamma rays. And here's the peak. It's very hard to see, so I'll just highlight it. It's supposed to be coming from the neutrons, emerging from the cold fusion. The only trouble was, this peak is at 2.496 MeV, and as I mentioned, when you detect this neutron, it's absorbed by a water molecule, and the water molecule recoils, and this peak should only be at 2.2 MeV because of the recoil of the water molecule. Now, chemists wouldn't know that, but a physicist would. And so seeing this peak as evidence immediately set off alarm bells. This is a gamma ray peak, by the way. And also the peak looks a bit dodgy. It's rather pointy, whereas all the other peaks in the spectrum, which come from naturally occurring background radiation, look more like peaks. So here's the evidence. Heat, neutrons, although somewhat dodgy, the wrong energy, gamma rays were detected sometimes, and the presence of helium-3 and tritium in the bubbles. Well, these we looked at very carefully. Millions and millions of dollars were spent in nuclear physics labs around the world, because this would have been a sensation if this was true. And unfortunately, the heat went away. It was very difficult to measure the heat accurately, because you had to take into account the energy of the gases being emitted, and you had to capture that and account for the energy very carefully, and that wasn't done accurately. The neutron signals that were detected by neutron detectors turned out to be just small heat fluctuations. These detectors in the lab are just air currents in the lab, because the neutron detectors they were using, they work fine when you get the flux of neutrons coming out of a nuclear reactor, a real nuclear reactor, but they don't work very well for these very low neutron fluxes. And also, none of the experimenters died. If we had got the neutrons coming out that were responsible for the heat that was detected, the flux of neutrons coming out would have given a lethal dose to everybody observing. Nobody died. Well, I won't say unfortunately, it would have been nice if it was a real effect. And there was evidence for fraud, because after that gamma ray spectrum that I showed you was published and the physicists pointed out, no, the peak is in the wrong place, they said, oh, sorry, erratum, and a new spectrum appeared with the peak in the right place. Gamma rays from neutron absorption in water, no, I'm afraid the peak shape was very odd, not seen in specialist nuclear labs who are used to detecting these peaks. And it was turned out that the deuterium they were using from their experiments is contaminated with tritium, because the deuterium was produced by electrolysis, which concentrates the heavy component of the water, and that also concentrates the tritium. So there's already tritium in the starting material, and you can make a molecule. This is hydrogen gas with one deuterium atom and one hydrogen atom, and that has the same mass as a tritium atom, and that also can fuse things. In fact, this department, the School of Physics, used to do a lot of experiments with heavy hydrogen, with deuterium, and it used to get its deuterium from the batteries of Melbourne's trams at night. Because the trams would be going around the city all day, boiling the water in the batteries. The light water would boil off preferentially, and so automatically concentrate the heavy hydrogen, which didn't boil so well. Other Australians got involved. These are a couple of my mates who I bet they wish I didn't have this, but this is John Bolderman, one of the architects of our synchrotron, a very much younger John Bolderman, by the way. And this is Nick Wesky, who's now working for the International Atomic Energy Agency. And they tried very carefully to reproduce the results, and they saw absolutely nothing. No nuclear processes whatsoever. However, just this year, some kind of American military lab using this apparatus claimed to have seen it again. It just won't die. And there's now a cold fusion session at one of these conferences, and when the organisers of the conference was asked, why are you doing this? They said, well, just in case it works. However, if we look at Bob Park's criteria for pathological physics, discoverers go straight to the media instead of publishing in the respectable journals. Yes. The discoverers said they couldn't release any more of their data because the hot fusion, thermonuclear fusion people were trying to suppress their work. Yes. The scientific effect was always the limit of the detection. Yes. It was only a very small peak, and there were other explanations. They didn't release the details. They only gave media interviews. There are only anecdotes. No, it was very little science. They said that it's credible because people have been working on cold fusion for 100 years, but none of the early workers made it work either. And they worked in isolation and didn't open their lab to physicists who knew how to detect neutrons and gamma rays. And in order to explain the way that water still produced cold fusion, they had to invent new laws of nature. So the last word on cold fusion is that there is not, nor has there ever been, any evidence of nuclear radiation produced in the cells commensurate with the levels of heat claimed. Remember, it would be very dangerous to have worked. Indeed, the strongest sign that it does work is the continued good health of the researchers. I just want to finish off with this last recent example, plastic transistors and organic superconductors. In 2000, there were these sensational papers appeared in the respective journals, plastic transistors, hundreds of different configurations, all of them outperforming silicon and much cheaper. And equally sensational reports of plastic superconductors outperforming conventional superconductors, are all appearing in the respectable journals. Well, this set the community on fire, and these are view graphs which I borrowed from a colleague who invited the discoverer of all these sensational things down to give a keynote address at the AIP Congress, the Australian Institute of Physics Congress, in, I think it was 2002. Unfortunately, the discoverer was otherwise engaged and couldn't come. And the reason why he was otherwise engaged is because people started looking closely at the published data, and these are three completely different plastic devices, and yet the noise in the electronic characteristics appear to be identical. So if I blow that up, you see this little wiggle, and this little wiggle. Here it's at different voltages, and that's impossible, because the noise is due to random effects, and here we're down in the noise. Why is the noise exactly the same? Two different devices measured, three different devices measured on different days, different configurations, different apparatus. Well, an inquiry revealed evidence for fraud. The guy who made these sensational discoveries was a lone worker and served two masters, one in Germany and one in the USA. When the Germans thought he was working in the US, he wasn't, and when the Americans thought he was working in Germany, he wasn't. No collaborator saw the work being done, therefore, as a consequence, because they each thought it was done in the other lab. No documentation was kept. The computer data was deleted to save disk space. This is at Bell Labs, the richest physics research lab in the world. And apparently he saved paper as well. We're not writing anything down. All these magic devices were destroyed by the measurements and were not available to be tested anywhere else. And even if they were, the few that were could not be reproduced by others who made new devices using the same method, even using the same equipment. And it was found the data had been altered by hand. They explained the same wiggles. Same data occurred in unrelated measurements, and the co-workers, so eager to get their work published in Nature, weren't sufficiently critical. And so in 2002, the journal Science withdrew 8 papers. In 2002, Physical Review withdrew 6, and the journal Nature itself, the pinnacle for publishing your scientific results, withdrew 7 papers. And the guy was sacked. Now, let me just conclude with these few more slides here on the characteristics of pathological science. Can I fire this up, Nick? There are many physics discoveries that obey some of the attributes of pathological science that we've studied tonight. And in fact, I was in the US when high temperature superconductivity was discovered, and I simply didn't believe it. It sounded like pathological physics to me.
The switch, Nick, the switch on the switch over there.
And here is, nevertheless, a piece of high temperature superconductor, the black stuff. It's a ceramic, it's not even a metal. It's got a little magnet on it, and of course, by now, classic demonstration, that when you cool this thing down, we get a strange quantum mechanical effect up here. And once we're cold, the quantum mechanical effect, called the Meister effect, appears in this ceramic. It's due to the flow of electricity through the superconductor, and this creates a mirror image of the magnet, the magnetic field of the magnet, and it's beautifully levitates. And this effect, which you hopefully will see in just a moment, is way, way above threshold. This is not, oh, there we go, up she goes. And of course, oops, and this effect works, by the way, in very strong magnetic fields for any non-quantum material, like a paramagnetic material, including liquid water. And so if you put a very strong magnet under the floor of this lecture theatre, because I've got a lot of water in me, you can levitate me. And I've seen, movies of frogs being levitated with this method in the bore of very strong magnets. And the labs who did that work received a letter from an evangelistic group in the US who wanted one of those magnets installed under the pool. So we're prepared to pay you millions of dollars for this, provided you don't tell anyone. And so, of course, the scientists in Holland, as it were, published the letter on their website. So this effect is unbelievable. I didn't believe it when I first heard of it, but there is an effect way above threshold. Unmistakable superconductivity in a ceramic. Who would have thought it worth a Nobel Prize, and it was. The other effect is, of course, Einstein's relativity. When Einstein put this forward in 1905, there was nothing available that went fast. And all the relativistic effects, Lorentz contraction, time dilation, only appear when you're going really fast. And there were no synchrotrons or particle accelerators in the early 20th century. And so you could have said that Einstein's ideas were pathological. However, there was one effect which somehow usually does not appear in our modern textbooks, which is, of course, the magnetic force. And so I can demonstrate to you the Lorentz contraction in this lecture theatre by making electrons move at only 1 millimetre per second down these wires made of aluminium foils, and the warping of space caused by Einstein's relativity creates a charge imbalance in the wire, and this appears as a macroscopic force when I energise and make the electrons move, only about 1 millimetre per second, and this is way above threshold. And of course, we now call that the magnetic force. So although both of these have elements of pathological science in them, they were unbelievable when they were put forward. Nevertheless, the effects in the right conditions are way above threshold. So let me conclude with Jamieson's corollaries. I would say that an example of pathological science is where when the proponent puts forward explanations that are impossible to understand. That's what I found during my term as president of the AIP. The papers that people were trying to get me to publicise, I just couldn't understand them, and that's either because I'm dumb or because it hasn't been explained well. So I'll let you decide which way around to put that. They often use traditional terms, new and inappropriate ways, and didn't address obvious inconsistencies with existing theory. They also typically tested their theories on the outcomes of experiments from long ago, and for some reason ignored newer experiments that gave more accurate data that might have been harder to understand. And the most important one, you need the unique conditions that prevail in the discovery's lab to demonstrate the phenomenon. And the discoverer typically works alone, isolated from mainstream science. Reproduction of the effect requires knowing his or her special tricks. So the phenomenon is his or her possession, not in nature. And above all, the data processing requires special tricks to pull the peak out of the noise. I would also alert you to Asimov's axiom. When people thought the Earth was flat, they were wrong. When people thought the Earth was spherical, they were wrong. But if you think that thinking the Earth is spherical is just as wrong as thinking the Earth is flat, then your view is wronger than both of them put together. Second stipulation. Extraordinary claims require extraordinary evidence. So if you've discovered a breakdown in the conservation of energy, then you've also discovered that the laws of physics change with time. And that is an extraordinary claim. You really better have very good data to justify it. And this arises from earlier statements of similar type. Extraordinary claims require extraordinary proof, or indeed from the great French mathematician Laplace, the weight of evidence for an extraordinary claim must be proportioned to its strangeness. That's a full claim, of course. And I'd like to conclude with one of my favourite quotes of all time. That is Occam's razor. Here it is in Latin, for you Latin scholars, but in English it's roughly, plurality should not be multiplied without necessity. The simplest explanation is most likely true. You could explain the crash of the flying saucer at Roswell by an interstellar civilization visiting us with some unknown inertial space drive perhaps to get here, or you could just say it was a weather balloon. I'm going for the weather balloon. Thank you for your attention.
Questions?
Sorry.
The characteristic of sections of graphs being reproduced on different experiments seems to recur quite frequently. Are these people just stupid, or are there some people out there who are not stupid and we're not picking holes in what they do?
Okay, that's a very good question. Why do something as obvious as alter the graph, and particularly use the same noise spectrum in half a dozen different papers? What happens is it creeps up gradually. And that's why it's very important to be rigid about adherence to ethical principles, because a small breach that may have no consequence at all, like just massaging the data to make a curve smoother or removing one data point because it didn't quite fit the theory, cascades and leads ultimately to the extraordinary pile of papers in that 3-year period, to tens of papers in the top journals, all of which were fraudulent. So they all started very gradually. And so you get away with it once, you get away with it twice, you get away with it 100 times, and then it comes crashing down.
Yes, you said earlier in the lecture elements 116 and 118 were discovered last year. What sort of experiments took place? Can you describe experiments, and how long did these elements exist in reality?
Okay, so the heavy elements, they're not quite the super heavies, by the way. They're maybe at the edge of this island of stability. There's still no clear way of making them, getting the neutrons in. They were made by crashing heavy elements together and looking at the reaction products and doing it over and over and over again. And most of the time, everything just fell apart. But in several rare occasions, a super heavy was discovered. It was captured down a beam line, and by the bend radius through magnetic fields, you could weigh it, and by the number of them that reached the detector, you could tell how long it lived from the flight time. And the lifetimes were typically milliseconds. So don't go building your house out of these things.
Well, if I could ask a question. The idea of zero-point energy has been around for a little while now. It's got good credentials. It was described almost 100 years ago by Einstein and Stern. It's been proven about 5 or 6 times called the Casimir effect. Now, efforts have been made to harness energy from it. How come it hasn't worked?
How come zero-point energy can't be harnessed to make work? First reason is the second law of thermodynamics, very disorganised. And all the schemes for harvesting zero-point energy, this is, for those of you who may not be familiar with the term, this is the energy that remains when you suck all the other energy out. This is in quantum mechanics, nothing is truly at rest. There's always vibrating a little bit after you've cooled it right down to absolute zero or done other things to it. People have dreamed of tapping into this energy and doing useful work with it. But it's the same problem with tapping the warm waters of the ocean, driving our civilization by cooling the oceans by a fraction of a degree. It needs work to do it. First of all, it's disorganised. But the second and more major problem is that in order to tap it, you have to find a lower energy state in order to transform the zero-point energy. It wouldn't be the zero-point energy if there was a lower state available. And so some people have claimed to find hitherto unknown lower energy states, for example, the ground state of a hydrogen atom, that's called the hydrino, but it's complete nonsense in my view. It would have much more serious consequences for cosmology and astronomy than producing some strange green compound in some guy's lab in the US. Notwithstanding the $25 million of investors' money, which may be the main reason why it exists, actually. So it was a bit of a confused reply. But,
no, that's good. Supposed to interfere with the focus of the cosmological constant. Who knows?
Okay, an opposite thing. Crop figures now. We've got absolutely unbelievably complex. They're all imperfect. We've got perspective in them now, Mandelbrot sets, the whole damn lot. Now, this physics department went like that 10 years ago when they were civil circle. Saying, it's all this complex water is. It's not a fraud, it's actually happening. What's your best explanation?
it's either alien civilization coming down and trying to communicate with us, or it's undergraduates from a nearby university. I'll leave you to draw your own conclusions to which explanation I favour.
I would like you to explain why an event which occurs 1 in 10 to the 14th time should be considered reasonable. And I remind you of Carl Revere, who claimed, I think, one of the top quarks, but on evidence that occurred 1 in 10 to the 14th.
Okay, so I guess basically the question is, how do you know when a phenomenon that is truly barely above threshold, as a 1 in 10 to the 14 event would be, is real and not pathological? The answer is you have to be very careful. In such an event, you have to look for it for a very long time to sift it out of all the background events. And in fact, I think it's true to say Professor Taylor here is making his career now out of sifting out just those events for the telltale ones that are going to give us evidence of Higgs boson and all the rest, in view of this enormous background of just garbage that's not useful. And so when you see how complex and how carefully worked out the detectors are that they're using to sieve out those background events, then you get an insight into how such rare events can be detected and how we can be confident they're real. But sometimes mistakes are made. The pentaquark was discovered a few years ago. The signal looked good. It was above the noise level, but more careful and more data considerations made it go away again. And that's fine. It's okay to make a mistake in physics, I must emphasise. But if you're going to make a mistake and then conceal it and not tell anyone, that's bad.
Well, on that, I think we should thank the speaker, David, very much. Just a reminder that next week is the last of the series. Andrew Malatos will be talking about direct evidence for dark matter in the universe with some very incredible figures.